Look at this. What you are seeing here is not real water. This entire scene is actually made from millions of tiny particles. Each particle follows a very simple rule. It only interacts with the particles directly next to it. But when thousands or even millions of these interactions happen together, something absolutely incredible appears. Scale this up to millions of particles, and suddenly it starts to behave exactly like a real fluid. Beautiful waves form, complex splashes appear, and the overall motion looks surprisingly realistic. In fact, simulations like this are now detailed enough to power modern Hollywood visual effects and deep scientific research. But behind all this beautiful motion, there is a massive problem. You see, every single particle constantly needs to know which other particles are close to it. And when you have millions of them flying around, finding those neighbors becomes an absolute computational nightmare. So, the real question is, how do we make this fast enough to actually work? Well, the answer is to stop searching blindly. Instead, we build a brilliant acceleration structure known as an octree. Normally, a regular grid divides empty space exactly the same way it divides water, which is a massive waste of memory. But an octree is like a living adaptive map. Where there is water, it dynamically divides space into smaller and smaller blocks. Where it is empty, it leaves massive chunks completely alone. Because of this clever trick, each particle now only searches its local neighborhood. The impossible global search problem is shattered into tiny, highly optimized pieces. To make it even faster, the entire fluid volume is wrapped inside tight, bounding boxes. Not a single byte of memory is wasted on empty air. And the result of all this mathematical magic, a system that is lightning fast and incredibly smooth. Looking at this performance heat map, the data flows beautifully, completely ready for the ultimate hardware stress test. Now, look at the core difference. The old simulation on the right quickly breaks apart into chaos. Particles collide, energy explodes everywhere, and the surface becomes unstable. But our Octree method keeps everything under control. Thousands of particles flow together smoothly, almost like a perfectly choreographed dance. And when we apply realistic rendering, wow! The baseline method reveals blocky grid artifacts everywhere. Sharp edges appear where smooth fluid should exist. But the Octree solution produces something very different. A surface that looks continuous, natural, and physically believable. No blocky patterns, just fluid. But here is the real secret behind all of this. Multi-resolution. Watch these squishy bunnies interact with the water. The Octree grid almost feels alive. It stretches and shrinks in real time, adapting perfectly to the motion of the fluid and the moving objects. Where detail is needed, the grid subdivides into smaller and smaller cells. Where space is mostly empty, it stays large and simple. This means the solver only spends computational power exactly where it matters. No wasted work, no unnecessary calculations. Now look at this double dam break. Here the simulation uses extremely fine particles near the surface to capture every splash and ripple. But deeper inside the water, it switches to larger particles that are far cheaper to compute. The result is extraordinary. The system can simulate 3.5 million particles almost effortlessly. But the ultimate endurance test is this endless fountain. Water keeps entering the simulation again and again. The particle count continues to grow without stopping. So why doesn't the CPU collapse under the pressure? The secret lies in a clever optimization technique called branchless programming. Normally, a processor must constantly stop and make decisions like a driver stopping at every intersection, but this algorithm removes those stops entirely. Instead, it builds a clean data highway where huge batches of particles move through the pipeline together. No branching, no hesitation, just pure data streaming through the processor at maximum speed, and finally, my favorite demonstration, multiple physics interacting in the same simulation. These orange armadillos are made from extremely viscous slime. They slowly deform and melt as they interact with the fast-moving blue water around them. Two completely different physical materials, two completely different behaviors, yet both are simulated together in the exact same space with incredible stability. That is the true power of this algorithm. Hold on to your papers. To understand this incredible speed, we need to look under the hood. Computers hate chaotic memory access, so the researchers reorganized the particles using something called a Z-order curve. This pulls the 3D world into a single linear ribbon of memory. Nearby particles in space are now close together in memory. This greatly improves cache locality and reduces cache misses. Next comes the traversal. Instead of slow if-else branches, the algorithm uses a branchless path through the octree. The CPU no longer stops to make constant decisions, the data simply keeps moving forward. Once aligned like this, particles travel in large batches, like cars on a high-speed data highway. Now SIMD instructions take over. One vector instruction computes many particle interactions at once. Not one by one, but many in parallel. And the result? Cache misses drop, while throughput skyrockets. The simulation becomes 2 to 4 times faster than before. And finally, look at this endless fountain. A true stress test for any physics engine. Water flowing frame after frame without breaking the simulation. But the beach scene is something else. 9 million particles, every splash, every drop, calculated with millisecond precision, a true symphony of physics.
What a time to be alive. If you enjoyed this, subscribe to Nova Visualized and tell me in the comments what I should visualize next. I'll see you in the next one.